So we've got this really strange result, the fact that you get discrete energy levels, particular wavelengths, and the only way we can think of to produce it is if electrons are actually not particles but waves, and waves trapped in a box, in this case the box being the atom.
Yeah, and that's not very obvious because when we look at electrons, and one of the places we see electrons are, for example, in an old style TV set which is a giant cathode ray tube where electrons come and hit the screen and illuminate things, and there you're really seeing individual particles hitting nothing like a wave at all.
Yes, and in sort of photomultiplier tube you fire electrons that you can see flash, 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 flash as each individual electron arrives. That sounds like a particle. The electron is here and there, not spread out, and waves by their very nature are spread out.
Right, so this sort of lends itself to a new interpretation, which is that the electrons themselves are some sort of probability description. So the wave is telling you where they might be at any given time, and when you measure them, suddenly you know right where they are on that little wave.
Yes, this is a really strange idea. The basic idea is that these are probability waves. So you get the waves, as long as you don't look at them, they are waves and they do all the interference and diffraction and standing waves that we need to get these discrete energy levels.
Right.
But as soon as we look at it, the amplitude of the wave, actually squared, tells you the probability that a particle is there. So you take the waves and you say, well, it's going to probably be here or probably there.
And there are these places where there's almost zero probability of there being, and that's sort of what pins the electron into a little place. It can't actually be there.
The classic experiment that shows this is what's called the two-slit experiment. You fire a beam of electrons at a board which has two slits in it. And you might think the electron would either go through one slit and land over there, or go through the other slit and land over there. So you'd see two stripes of little flashes along there. But in fact, as long as you don't look, what you actually see is a series of interference waves all the way along here. So it looks like the particles, even when there's only one electron in the system at a time, as long as you've got two electrons interfering with each other, you can have it so there's only one electron in the whole experiment at the time, and it still seems to go through both slits and give you the interference pattern, which is totally weird. Let's go over this two-slit experiment in a bit more detail. So let's start off with an electron gun over here and a phosphorescent screen over here. The electron gun is firing out electrons in a range of directions. Now what would we see here? What we'll see is when each electron hits the screen you get a little flash. There would be a flash there, then a flash here, then a flash there. More flashes in the middle, fewer towards the outside. Now because each electron produces a flash, it looks like the electrons are just single particles. Electron is here or here. It's not spread out in some way because you're definitely seeing definite flashes. But overall, the flashes are more likely in the middle and less likely at the outside, so you get some sort of probability bigger in the middle and smaller as you go away. Now what would happen if you put a slit, a mask in front with two slits? So there's one slit over here, and then another slit over there. Now what you would expect, common sense would tell you, is that like electron that hits there won't get through, electron that hits over there won't get through, electron that hits there won't get through. The only ones that are going to get through are the electrons that go through one of the slits. So what you'll see is a bunch of flashes over here, electrons that went through the top slit, and a bunch of flashes down there from electrons that went down the bottom slit, and all the other electrons are just going to bounce off or get absorbed by the screen. That's common sense. What do you actually see? Well, what you actually see is the most flashes occur about here. And you also get flashes appearing there, and there, and there, and there. So you get a series of waves of flashes. So you get flashes here, 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 etc., but not in between. No flashes halfway between there, halfway there, halfway there, halfway there, halfway there, halfway there. Which is weird, right? How can an electron fired out from here get through these slits and go there? And if it does go there, why isn't it going just next door over here? Why is it here but not there? Now this all makes sense if instead of electrons we were talking about a wave, like radio waves. If we're looking at radio waves, you can imagine them spreading out from here. And then as they go through this aperture, they start diffracting out, so you get waves coming out from that aperture, and the same from here. Now if you are exactly halfway between, the waves have to travel the same distance here as there, which means all the peaks of the waves are going to line up. so you get strong constructive interference. But if you go a bit to the side, like over there, the waves from this slit have a bit shorter distance to go, the waves from this slit have a bit of a longer distance to go, which means that the peaks from one will line up with the troughs of the other, so they'll cancel out and get nothing. So this pattern, signal, no signal, signal, no signal, makes sense if electrons are waves, but it doesn't make sense if they're particles. But that's the puzzle. What we see at the screen is a flash, like it arrived there, it arrived there, not some sort of wavy thing. But how can particles behave like waves? And that's where the idea of the probability wave comes in. That they are waves as long as you're not looking at them. And so they do all the interference things. And so the amplitude of the wave will be strong here, and low there, and strong there, and low there, and strong there, and low there, and so on and so forth. Just like you get for radio waves. But then as soon as you actually observe, it collapses the wave function and you get a definite spot at a different place, but the probability is given by the amplitude of this. So there's a high amplitude there, so there's a high probability of getting a flash there, low amplitude there, so low probability of getting a flash there. Pretty weird.
So Schrodinger came up with a sort of an analogy, which he called this, well, we now call Schrodinger's cat. So you can imagine if you have a cat, so I do have a cat, my cat's name is Rodney, and you put him in a box, and in the box you put a very sensitive, vial of poisonous gas that may break, with some probability. And you don't know if that event has occurred until you open the box to see if Rodney is alive or dead.
So according to quantum mechanics, until you open the box, what's inside is not an alive cat, a dead cat, but actually 1 over root 2 dead Rodney and 1 plus 1 over root 2 alive Rodney, two waves interfering with each other.
Right, so there's a probability he's dead or alive, and you can figure out that probability because what you do is you have more than one Rodney and do the experiment a billion times. You realize that 52% of the time Rodney's dead and 48% of the time he's alive.
Yeah, and this whole business about when you don't know it, it's behaving like a wave, I mean, that sounds ridiculous. Maybe, surely that really is a live or a dead cat. But like in the two-slit experiment, the fact that you don't know where the particle is allows it to go through both and interfere with each other. So you could get some sort of strange interference effect between alive and dead Rodney, which would give quite different results.
Right, and when you open the box, then you know, and you know what's going on, you've collapsed the probability down to a value.
Now, a lot of people, myself included, don't like this very much. I mean, why should it matter whether someone's watching? Electrons do one thing all by themselves in the privacy of their own room while no one's watching, but as soon as you look, suddenly everything collapses. I mean, what is it about us that makes it collapse? Is it something about the human brain or something? For example, can Rodney observe itself? It's very uncomfortable, but it actually seems to be how quantum mechanics works, and you just have to live with the discomfort of it.
Yes, I have to admit I do not find it easy to deal with either, but it is a way that describes the universe that we live in.
So, quantum mechanics is weird. It's telling us that things are behaving like a wave when no one's watching, but like a particle when we watch. And it turns out that is one of the crucial clues to explaining white dwarfs. Now let's go back and talk about the other two crucial clues that quantum mechanics gives us to explain how a white dwarf can survive this immense pressure.